Hi, I'm Ryan Nickel, CTO at DSA Ocean, and today I want to talk about tuning the autopilot controls for seakeeping and maneuvering in the ProteusDS ShipMo3D toolset. For this, we're going to use one of the sample projects, the generic fishing vessel that you can download off the ProteusDS.com website. And you can see, of course, there's a rudder at the back. And that's one of the model components in build ship here when you're assembling the final ship model. When you add the rudder, if we just go to edit rudder here, in addition to the location and the geometry, span, and all of those effects, there's other autopilot control parameters here. So maximum allowable deflection of the rudder, and more to the point, the heading gains. These are the parameters that I wanted to focus in on. So these are the default values when you make when you add a new rudder. And this heading gain is basically a stiffness term where the more the heading of the ship moves away from the desired heading, this term is going to govern how strongly the rudder is adjusted to move it back. And similarly, there's a heading velocity gain. It's kind of like a predictive damping term. The higher the velocity of the heading is away from the desired heading, the larger the rudder correction will be to try to make it come back again. So why do we care about these parameters? The issue is if they are too aggressive, then it may actually exacerbate ship motions. You may get more roll motion, especially on a smaller ship that's more susceptible to how big the forces could be from these things. So now I have named this build ship configuration called a stiff rudder for a good reason. We'll see shortly. But maybe you have no idea what the implication would be behind this, and you just want to gauge what's happening. So what we're going to do is we're going to go and we're going to open SeakeepRandom. I was playing around with this earlier. Ship motion database file name. So which model do we want to work with? Let's make sure we're picking the stiff rudder that we made in build ship with the control coefficients that I was referring to. We're going to be looking at a sea state a spectrum with a 7-second peak period. That happens to be really close to the roll natural period of the vessel, so we'll get some exciting motions, and we'll run it. Let's see what happens when we do a frequency domain analysis here. So when we look at the RMS motions from all the different sea directions in this sea state, this is great. We get a good idea of what's happening with the ship motion. And what I want to draw your attention to is, well, we also have a rudder RMS indicator here. So this is at 0 speed, and it's kind of indicating, 10, 11 degrees rudder RMS. Well, I mean, it's not near the maximum 35 degrees, but that's kind of a lot of motion too. Well, what happens if we look at higher speeds? We're kind of seeing the rudder action go up, and at the highest forward speed, it's 20 RMS. Now remember, this is RMS, so there will be peaks bigger than this, right? So it's kind of giving an indication that this would be quite a lot of rudder activity. So this might be a sign that something is wrong. We're getting like pretty big RMS values. The other thing that you can do to check is a time domain seakeeping analysis. Now I've run some cases already. So I'm going to go to add existing data. The seaway that let's just take a quick look at that. The seaway that I've set up for this is the same as in SeakeepRandom, spreading function and 7-second peak period, and it's coming from 30 degrees off from 0, just to make a nice bow quartering kind of condition to get some roll motion in there, and trigger some heading variations as well. So we'll go to open this data set here, a FreeMo case with the stiff rudder. So we'll open that. Now, again, I've already run this analysis. If we look at the trajectory, it's run for an hour, but even here you can kind of see there's a bit of zigzagging, a little bit of zigzagging back and forth. Okay, maybe there's nothing wrong. We're not totally sure about that. If you look at the displacement plot for this, you'll see, quite the first thing that might stand out. Well, we have got heave and roll motion, pitch motion. Okay, but there's quite a lot of heading variation, plus or minus, 50, 60 degrees. Like that's kind of swinging around a lot. So that's a sign that maybe something is wrong. Maybe the rudder is too stiff, too responsive. The other thing that you can do that really sets a clear picture is plot rudder prop that shows the rudder and prop behavior. And here we really see the rudder angle is pretty much swinging all the way back between extremes 35 and 35. So, the issue here is that, for this size of vessel, that much rudder action might actually be exacerbating roll motions. And, and indeed, if we look back at roll here, we're seeing sort of plus or minus 16, some maximums around there. So let's see what happens when we dial back on those gains. So I'm just going to close a few of these here. I want to load a different set of FreeMo data, so we'll exclude that. What I'm going to do is in SeakeepRandom. Now, all I did was I made a new build ship project where actually I can show you exactly how that's different. We'll go to here and exclude the stiff rudder. I'm going to add some existing data just so we can look at it of the normal model. The only difference with this one is that we just reduced those gains by a factor of 2. So instead of -4, it's -2 here. Instead of -8, it's -4, just to see what happens. It was a sensitivity check, right? So let's go back to SeakeepRandom. Now we're going to rerun this SeakeepRandom, not using the stiff rudder, but this other ship model with the better coefficients, as we'll see shortly. So we'll run that, recalculate everything, and now when we look at the RMS motions, we get some slightly different variation in the RMS motions. But notice the rudder RMS is now around half. It's 5 instead of 10. And at forward speeds, before we were seeing as high as 20, now it's 11 and going down from there. So a good sign that the rudder is less active. Okay, and then we can also verify this with a time domain seakeeping analysis, which again I've already run this ahead of time. But if we load that, now I can show the plots. So again, showing the trajectory. Wow, that's a nice straight line, and instead of something with quite a bit more zigzag to it. So we plot displacement, and we're still seeing heave motions, still seeing roll motions. Heading isn't going between plus or minus 50. It's more like a few degrees, which looks much more reasonable. And in terms of the roll motions, it's 10, 8, plus or minus 10 instead of 16, 17. And the last plot here in the time domain seakeeping analysis, let's look at the rudder prop output. Yeah, there's some extremes here and there with plus or minus 15, but generally, it's sort of within plus or minus 5 degrees, which is much more reasonable. So it's not a stiff rudder. So, that is to say that it's not obvious what the right gains are going to be for your ship. But it's pretty quick and easy to change them, and then do some quick investigations in frequency domain, and if you really need to, double check things in the time domain. And depending on the ship configuration, it can, if you've got a really aggressive autopilot, it can increase ship motions as well. Thanks for watching today.